Thank you, everybody, for coming. And I'm Rakesh Jain. I'm from IBM and also part of Soda Foundation, which is an open source data management platform. It's actually a bunch of projects under Soda Foundation related to data and data management. My co-presenter, Sanil, is not here today. He couldn't come. He's in India, actually, so he couldn't get the visa or whatever. So multiple reasons he couldn't come. But so I will be taking you all over this topic about container data protection, going beyond CSI. And please feel free to ask any questions anytime. Before we start, anybody here from CSI working group, from Cube Storage, SIG Storage? No? Okay. All right. So let's get started. So we'll go over certain trends in cloud native storage, and then we'll go into the efforts in the cloud native data protection side. And then we'll get to a specific case of using storage systems-based replication in container orchestration systems. So, I'll try to keep it to the point. The last topic is the one where I want to spend most of the time. So first, what is happening? The cloud native storage landscape and the trends. And before we go into that, so let's just get to the same page here. There are a lot of terms. When we talk about cloud native storage, we're talking about a type of scale out software defined storage, which is actually deployed on container orchestration system like Kubernetes. So basically, you are building a storage system based on, deployed on Kubernetes. Now, this can serve Kubernetes-based applications, or this can serve non-Kubernetes-based applications as well, something like as a service. So that is cloud native storage. When we talk about CSI, CSI is container storage interface, which is actually a specification coming from SIG Storage, which is actually a special interest group related to interface of containers with storage systems. And then, different storage providers actually use that specification. So that's the the terminologies we will be using. In terms of the ask, basically, the ask has been like this. Just the things are growing and changing. We want unified data management across edge, core, cloud, whatnot. Whether it is file storage or block or object, and any type of application or platform. So that's the overall requirement has been there for a while, and of course all the vendors are trying to meet that. As part of Soda Foundation, which is actually part of Linux Foundation, we do a survey every year. And this survey actually is targeted towards CTOs, CIOs. And the questions in the surveys are mostly related to storage and where they think they will be spending most of their time and money in the next few years. So this survey actually conducted last year. In fact, this year also the survey is conducted. It's complete now, but we don't have the results yet because Linux Foundation research team actually is compiling the results right now. So that should be out sometime in October or November timeframe. But from last year's survey, what we find here is that there is no surprise, actually. You probably know all this. There has been a move towards container-based environments from VMs to containers, and it's growing rapidly. Kubernetes is, of course, the topmost deployment platform right now, whether it is cloud, whether it is on-premise, or even on the edge. And container storage is real. It's real for whatever reason, but it is real. People are using it in production. And if you look at other surveys available, I think the trend is pretty much similar. Use of containers is growing. That's the key here. In terms of solution trends, basically, what the companies are doing, what the vendors are doing. So the focus right now is that vendors are actually working to build new businesses around this new ecosystem of containers, which can provide end-to-end solution in terms of data management. So that's the key takeaway. Whether they are doing it based on whatever storage systems they have available and add features on top of it, or add features outside of the storage system, for data management. So that's more or less what's going on. Especially, there is no standard in the field right now, especially when you deal with containers. The standards are actually evolving, but very slow, and the requirements are coming up from all over the places. So vendors have to do something, right? So that's the trend right now. And if you see the cloud native stack, basically, if you see the blue layer, that's where all the container stuff is coming. The container storage is there, network runtime, everything. And on top of that, you have your applications and middleware running. For storage, the storage can come from the host themselves, which is basically the cloud native storage, or the storage can come from the storage boxes, the storage systems which are outside of this thing. So that's what I just want to convey here. But yeah, this is the whole stack. Now, in terms of the projects themselves in the cloud native world, I don't know if you have seen, probably you have seen another landscape from CNCF about the cloud native stack itself, not just storage. And that one is 10 times denser than this, probably. So this one, actually just telling you that what are the companies involved in storage projects in the cloud native environment. So you see a bunch of them, and they're doing, pretty similar thing, more or less. The ones which are circled here, these are actually part of Soda Foundation ecosystem. So they're called eco projects. But more or less, yeah, this is the current landscape, and this actually is not complete. We may have missed a few companies as well. So what the platform vendors are doing, so we did a little bit of analysis on the different vendors which are actually in this field. And sorry if you can't see this, this is quite small. But just to summarize, there are a lot of players. What we are trying to do here is that we try to map what requirements they are meeting in terms of what features they have, like snapshot, migration, and whatnot, and whether they are open source or not, and yeah, what kind of storage they are supporting, meaning file or block or object, right? The key takeaway from the previous slide is that the product direction is inclined towards hybrid cloud data management right now, using the cloud native storage. And then the data protection and mobility are the two key key asks in that field, and all the vendors are working in that field. So basically, backup restore is kind of primary use case in the data protection domain. Now, what is happening in terms of data protection efforts in the Kubernetes world in general? So Kubernetes has this SIG storage, as I mentioned, which deals with all the data aspects. And in that SIG storage, there is a work group called Data Protection Work Group. This work group is responsible for doing all the CSI, not all the CSI, but just the protection part. Now, what is the current state of this work group? What they are working on, what they are looking for, right? So the focus right now is on backup and recovery. They want to do application level backup, meaning that an application deployed in Kubernetes, you can back up the whole application, which includes the application metadata, meaning application configuration, application containers, all that, and application data, right? So that's the focus, that you can completely back up your application and completely restore it. Restore it in the same cluster, in a different namespace maybe, or in a different cluster, right? So that's key. Other is namespace protection, which is basically you have maybe multiple applications or partial application deployed in a particular namespace, and you want to just back up that namespace and restore it elsewhere. And the third one is cluster protection. Whole cluster, whole Kubernetes cluster, you want to back up and restore elsewhere. So that is their objective. And where they are today, right now they have volume snapshot API. So basically, which allows you to snapshot a particular volume within the same location. Basically, as you know, snapshot is within the same, if it is stored system, it is in the same stored system. So that is what is available today. In terms of application itself, they have this thing called custom resource definition, which is basically, you can represent an application. It's an extension to Kubernetes. For example, if you're deploying, let's say, Cassandra, you can create a custom resource definition for Cassandra. And you can actually see the status of Cassandra, for example, using the kubectl command and whatnot, and deploy it as a CRD. So right now, this is actually very little compared to what they want to get to and what actually people want. But I mean, they're going in the right direction. But yeah, it takes time because it's a specification. It has to deal with lot of existing setups and the vendors, right? And a lot of expertise there as well. So what is missing is, for this particular use case of backup and recovery, what is missing is the backup itself. Right now, there is no volume backup. And okay, so what is the difference between backup and storage here, and the snapshot? Backup is actually a point-in-time copy as well, but it is in a different location, not in the same location. Second thing is backup repository, which is where do you want to keep the backup, because it is in a different site, right? Or different location. So backup repositories are missing, backup itself is missing, and the volume populator. What it means is that you want to restore, right? So you want to restore from a particular repository where you have put the backup, right? So this is how you will actually restore, through something called volume populator. So yeah, they're working on this. Then there are pre and post backup hooks, which will actually tell you what to do before backup and after backup, like Quasec. Incremental backups are also missing right now. That is very important. And another important thing is the consistency group-based backup and even the snapshots. So consistency groups are missing. And all this actually will lead to final thing of doing the application level snapshots and application level backups. So right now the focus is on this. They're working on this and then working on the CSI spec itself to incorporate these things. Now, given that these things are not there, there are multiple projects which are trying to fill in this gap. And some of them, and not all, some of them are listed here. One is Valero it's an open source, but it's from VMware. There is Canister, which is from Kasten.io. And I think Kasten is acquired by some other company now, Veeam. There is this Red Hat OpenShift Data Foundation, which is based on Rook and a Ceph. So these are actually Ceph clusters. And Kahoo is another one from Soda Foundation itself. And I'm sure there are many more. So speaking of Kahoo, so before getting into Kahoo, so Soda has this, as I mentioned, it has multiple projects, right? So it has this project called Soda CDM, which is Container Data Management. This basically includes, this is open source, so you can go on the Soda Foundation website and see everything, what it is doing. But at high level, this is for container data management, which includes data protection, data observability, data mobility. We're trying to align completely with CSI as much as we can. But until the CSI is there, we have our own extension. So we do use that, basically try to do our own. And then as soon as things are available in CSI, we will move to that. Supposed to support heterogeneous storage systems when they are available. And very important in Kubernetes world right now is multi-cluster and federation. So multiple Kubernetes clusters, right? So the vision is that we should be able to get to that as well. Not there yet. And then hybrid container data management. So especially when you're dealing with on-prem and cloud kind of setup. So this is at high level what is Soda CDM. And Kahoo is the first project under CDM, which is backup and restore. If you look at the features, I think we are trying to do pretty much the same thing. The only reason you would have new projects coming up is because you have an ecosystem and you want to integrate with that ecosystem. And with some other projects, you are not able to do that, right? So that is one thing. And then the future roadmap, which do not align with other projects and things like that. So you see, and this is the reason why we should have some standard specification. And this one actually is listing all those kind of features, basically. So we want to do the same thing. Back up your application, which is application metadata, and back up your data itself. So data backup and restore, and application backup and restore all together. And as much as you can do with CSI. The interesting features there are, apart from scheduled backup, you can do backup based on event-driven characteristics or requirements, and based on policies. So that is something important. So I won't go into any more details of Kahoo, but I want to get to the point where we talk about, now we can talk about the storage systems based replication and how to use it with the containers. Storage systems have been around for quite some time, serving, mission critical applications and whatnot. They do efficiently store the data, provide data resilience, protection strategies, everything, right? So, and all these features, right? Snapshot, deduplication, compression, tiering, thin provisioning, encryption, everything. So quite robust. People are building other kinds of storage now, which is fine. But if you have something available, why not use that within your ecosystem? And one more thing, I have seen cases where you are installing, let's say, Ceph cluster on virtual machines because you want to provide container-based storage, to either containers or to VMs or whatnot, right? This Ceph clusters installed on VM are actually taking storage from where? From storage system. So what's the point? There might be commercial reasons, but just get to the basics. Why do you need something? So anyway, I mean, there are certain arguments there that it's portable across the clouds and across the systems. You don't have to depend on the same storage system on both sides. Yes, but then you also have to look at the performance and all that. Anyway, I'm not here to actually discuss pros and cons, but let's just discuss about what we want to get to using this particular aspect. So storage replication. As I mentioned, data backup is basically point-in-time copy. So whatever reason you use them, whether it's regulatory or archival purpose or nowadays cyber resiliency reasons, data replication is basically continuous copy of your data from one location to another location. And this can be synchronous or asynchronous. Right, so let's see a couple of examples. Metro Mirror is one example where you can do replication from one site to another site. This can be synchronous as well as asynchronous. Especially when it is synchronous, the requirement is that it should be, the sites should be less than 30 kilometers, or 300 kilometers. The example I'm giving here is for a set of storage systems from IBM, but doesn't have to depend on vendor. It is across, pretty much similar for different vendors. For example, Metro Mirror single direction copies data from site 1 to site 2 in single direction. Metro Mirror failover failback is both directions. So you can failover and then failback. Failover failback with practice volume. What it means basically is that similar to failover failback, meaning that you have data going on from site 1 to site 2, but in order to test your replication and recovery, you have a practice volume or a set of practice volumes, which is basically a flash, the snapshot of what you got on the second site, so that you just work off the snapshots and you don't disrupt the replication. And then you can have multi-target as well, so you can have the data going to multiple locations. Similarly, there is global mirror, which is for larger distances, greater than 300 kilometers. Same stuff here, single direction or multi-direction with change volumes, where change volumes are basically volumes where you have a snapshot on the source site, and then the replication happens from the snapshot to the target, and then there is another snapshot there, which would actually create another change volume. Then there is same stuff here, practice volume as well. So two direction in the practice volume, and then practice volumes on the both sides. So these are some examples of replication which are quite robust and have been in use for quite some time. So what we are trying to do now with Kubernetes. Now at the bottom, if you see, there is storage system which is doing the replication from site 1 to site 2. On the left side there, you have the Kubernetes cluster, which is actually running some application with the pods, consuming data from the storage system down below. When you replicate the data to the second site, how do you recover there? And our goal is that we want to recover as fast as possible. So that's the problem we are trying to address here. So before we go into that, let's just get to the basics. So we have multiple microservices running in the cluster, in the Kubernetes cluster, and some of them use the storage from the storage systems, right? So in Kubernetes, what we have is that, let's say there is a pod 1, which is using data from SV1. SV1 is the storage volume. And the way it does is that it has something called PVC, which is persistent volume claim, which is basically a request for volume. And once it has this PVC created, PVC will be seen by the storage driver, which will actually create PV1, which is going to bound to PVC1, for example. So pod 1, PVC1, and PV1, and SV1. This is basically the connection, which actually gives pod 1 the volume SV1. All right? And right now we're talking one-to-one only to keep it simple. So this is basically how you have the storage consumed by the pod in Kubernetes. All right. So what we want to do is that when you actually, let's go here. When you actually have this set of volumes on the left side there, let's say SV1, SV2, SV3, there will be a replicated set of volumes. Let's call them SV1 dash, SV2 dash, and SV3 dash, right? So that's the pair, basically, the replicated volumes. And what we are trying to do now is that we want this copy relationship is maintained within the storage system, right? So we are going to use this mapping, which is available on the source side itself. And then on the source side also, we have another mapping, which is between pod, PVC, and PV, right? So basically, we have a mapping of pod, PVC, PV, SV, and SV dash, all available on the source side. And we use this information on the target side as well, so that we know that what is the SV dash we have to use on the target side to align to the pod to be deployed on target side. All right. So it may be confusing. Please feel free to ask a question. But our objective is that we have SV dash on the target side, and we want to make sure that this SV dash goes to the right pod on the target side, so that we have the data available right away on the target side. Okay, so in order to do that, let's just see how the request is made for the volume. So if you look at this, on the left side, there is this PVC, which is persistent volume claim. And this is how the request is made. In there, you have the storage class name there. Let's call it replicated storage class 1, whatever the name of the storage class. And that one is requesting 5 gig of storage. So that's the kind of request which is sent by the pod to the driver eventually. And how does it reach the driver? It's through that storage class. So let's see how the storage class looks like. The left side, again, the storage class is basically telling that who is the provisioner, which is your driver. And then there is a set of parameters for that driver, okay? So it is the same driver we are going to use on the source side as well as on the target side. But on the source side, we have a different set of parameters than on the target side. On the source side, we actually tell that what is the replication role of the driver. In this case, we call it, let's say, call it source. What is the replication type? So this will actually tell, metro mirror and any properties of that replication. If there is a consistency group, we also tell what consistency group it is going to use. And then what is going to be the target? So we are telling the target is your south one, which is probably this one. And then there is something called metastore address, which is actually a object store, which will store this kind of mapping. So this is what we are telling. And on the target side, same stuff, but the role is now target. And we're just telling that what is going to be the source. And same metastore, right? So this is the twist here, that you have the same driver, but it has different roles on the source and the target. And what is going to be the behavior of our driver? So look at the source side. Now, driver knows, because of that storage class definition, that I am on the source side. And when a create volume request comes through a PVC, what it is going to do? It's going to create the volume on the source. It is also going to create a volume on the target. And it will set up a replication relationship between the source and the target. So that is all information available in the storage class. Then it will create the persistent volume object in Kubernetes, which it does because it is the driver. And basically, the PVC will be bound to that volume. So now, with this request, we are able to create not only the source volume, but source volume, target volume, and the replication relationship between them. In addition, what we do is that we have this whole mapping of PVC to SV and SV dash, and which cluster it is coming from. So all this mapping we put in that replication metastore. Now, on the target side, what do we do? So suppose, so let's say, source side is done, everything is fine, and the data is getting replicated to the target. So SV dash is there. On the target side, let's say you deploy the code you had on the source at the target also. Now, this is where you want to actually bind your parts to the right set of volumes, the SV dash ones. So when you deploy the code, you will have the PVC request coming in for the driver. Driver will look at this and say that, okay, my role is target, right? And because my role is target, my first job is to get to the replication metastore and get the mapping. So I get the mapping of source cluster, PVC, PV, and SV and SV dash. The request has come from PVC, so I know PVC. Now I have to find SV dash, so which volume actually I want to assign to this PVC. So because I have this mapping and I have PVC, I already have the mapping now, so I have the SV dash information as well. So when you actually are dealing with the create volume request on the target side, you're actually not creating a volume, but you're picking the existing volume, which is SV dash, and returning that to Kubernetes so that the PV created by Kubernetes will actually map to SV dash, which is the target volume, which has the data, and that one actually will map or bind to PVC. So basically, now you have assigned the SV dash to the persistent volume claim request. And this is where you actually have the setup where SV1 and SV1 dash mapping is there. So pod 1, when pod 1 is deployed on secondary site, it will be mapped to SV1 dash. And likewise. Yeah? Yeah, no, good question. Okay, so the question is why the source is creating the volume on both the sides rather than the secondary side volume is created by the driver on the secondary side, right? Okay, I guess so both options are there. Either the source creates the volume, or the source actually calls an API, because volume has to be created on the target side, right? So the source will actually tell somehow the target side to create the volume. So whether you call the API or whether you and tell this, in fact, that's what you do actually. You call the API to create the volume on the target side. You can't create the volume from the source side. We actually did the similar thing when we were dealing with OpenStack and Cinder. So in fact, that implementation might still be there, that you call the API on the target side to create the volume. Yeah, right, yeah. Okay. Yeah. So that is the mapping, basically from pod to SV1, and then that when this site goes down, you have the same mapping actually created on the target site. I'm actually showing here, you use the DevOps and GitHub mechanism to deploy the code, but there are other mechanisms like, application and the Metastore backup, right? We talked earlier. You can use that option as well, whatever makes sense in your case. The key here is that everything is done at the driver level, right? Yeah, so this is basically the flow chart. It actually tells very clearly how this solution works. Whenever there is a request for creating the volume, the driver actually checks whether I'm source or I'm target. If it is source, it will look whether it is for create volume request or update volume or delete volume. If it is for create volume, I think we just discussed, you have to do created source, call created target, set up replication relationship, and then return and store the information replication metastore, which is very important. Similar thing happens for update, and delete is important because for delete, you actually have to not only delete the volume on source, you have to delete the volume on target, and before that you have to remove the replication relationship. So that's, and then if there is a consistency group, you have to take care of that as well. But the key here is that you actually are taking care of all the cases. You're taking care of single volume, but you're taking care of consistency group also, which is very important. Without that, single volume actually doesn't make much sense. When the role is target and the request is create volume, usually it is create volume only, right? Because you're just deploying and then this is your failover, right? So it just checks the role, whether I'm on target, and then it will go to the replication metastore first and get the mapping and do the right without creating volume, it will actually return the existing volume so that you have the data available to the pod itself. So yeah, that's the key. I think I just wanted to show, you use your existing storage systems because you already have this in your environment in most of the companies, and how you can best use it for a very quick disaster recovery for your Kubernetes-based applications. And I guess, yeah, that's it. So thank you. Any questions? Then you have our early lunch. Yeah.
Has there been any discussion about how to kind of create backup kind of volume? I don't see a lot of backup players here. Maybe an immutable volume that can get the ransomware or something like that. We're talking a lot about mirroring here.
Yeah.
One use case.
There, I believe there are some recent announcements actually from, and I know IBM, so I'll tell about IBM, about that kind of setup for cyber resiliency. I don't have too much details about it. I saw in the news also, but I don't know internals whether it is based on I think it is similar that you eventually have a snapshot. There is also there is some work going on about doing anomaly detection on the backups. This is actually a machine learning based solution, but you can actually see the behavior on your backups and then figure out that there might be some anomaly in the backup and it could be affected.
Yeah, that's pretty common. It seems like it's kind of different, a lot different than the way like a backup vendor interacts with VMware. Is there any discussion around things like change log tracking kinds of filtering things that VMware supplies to backup vendors? Kubernetes. I'm not familiar with the Kubernetes.
There is no, I haven't come across, because as I mentioned, in Kubernetes world right now, the focus only is on standard backup, because that also doesn't exist. So I think that will come following up after that, but right now, no. Okay, nothing else, I guess. Thank you very much for attending, and you have early lunch.